Firstly, we must create the bus. So for bus 1, we set the nominal voltage to 13.8, PU value of 1.0 with 0° phase. And also don't forget to set bus 1 as our system slack bus. For bus 2 to 6, we will set the nominal voltage to 230 kV. Why? Because they are at the secondary side of T1, so the voltage from bus 1 will step up to 230 kV according to this calculation. Now since they are PQ buses and we don't know their voltage value, that's why we set it to 1.0 with 0° phase PU as our initial voltage value. Then for bus 7, we set the nominal voltage to 15 kV. We calculate the absolute voltage PU as 1.0 as shown here, and since we don't know yet its phase angle, we can just set it as 0 degrees as our initial value. Next, we insert our generators. So G1 at bus 1 will have MVA base of 100. Connected to slack bus, we can simply put any value for our power set point. In this case, I put 100. Connect G2 to bus 7 and set the MVA base to 200. We set the megawatt set point to 180, while for MVAR, we set the min and max values as negative positive 87. Then we insert our transformers. So for T1 is between bus 1 and bus 2 and set the series reactance as 0.1 pu and set the MVA rating to 100. Meanwhile, T2 will be between bus 6 and 7, the series reactance will be 0.05 pu and the MVA rating as 200. Next, we insert our transmission lines. So for that, we need to input the series resistance, series reactance, and shunt charging values of each line based on these calculations. Lastly, we add loads to our PQ buses, bus 2 to 6 with constant power of 50 MW and 30 MVAR. We are basically done with our diagram, but additionally we can add bus fields to visually show the nominal voltage, PU voltage, and phase angle of each bus.
Go under the Tools button, make sure it's under Run mode, and then we press Solve Power Flow Newton. So now we'd like to display our results. How do you do that? So first we go to Case Information, and then we press Custom Case Info. So now we would go to the Explore section. First we need to check for Generator section. Okay, so in this section we can see that there's bus 1 and bus 7. 1 represents slack bus while bus 7 is PV bus. So in this section we can see the active power and also the reactive power. So what we need to make sure is that for the PV bus, the minimum value is set to negative 87 and also maximum as 87. So now we are at the bus section. The bus section, first we need to find out our voltages in per unit form, and also need to find out the phase angle for each of these bus 1 to 7. Next, in branches input, we verify the R, X, and B values to confirm the correct line and the transformer data used in the simulation. Now in the branches state, we look at the active and reactive power flow through each line and transformer, and also observe the power loss to understand how much energy is dissipated along the network. So this gives us the line flows and transformers flows.
To increase the voltage in bus 4 by about 5%, we tested two different methods using the Newton-Raphson power flow and power word simulator. Method 1, we increased the set point voltage at both generators and we adjust the reactive load at bus 4. This raised the voltage in a moderated way. Method 2. For method 2, we added a shunt capacitor at bus 4. The capacitor provides local reactive support, which reduces the reactive burden on the generator and lower losses. For our case, we chose method 2.
The reason of choosing method 2, let's compare the result first. As you can see, the formula for the percentage increment is equals to output voltage from case 2 minus with output voltage from case 1 divided by output voltage from case 1 times with 100%. The output voltage at bus 4 from case 1 given is 0.91752. By using the formula, the increment percentage from method 1 ranges from 5.88 to 6.25%. Meanwhile, for method 2 ranges from 5.01 to to 5.05%, which is the closest to the requirement condition, which is increasing by 5%. The reason why we choose method 2 is because it directly involves at bus 4, so the voltages in both generators remains the same, which causes the output of the reactive power in both generators are lower than method 1. By adding the shunt capacitance, it reduces the reactive power load by reducing the reactive current in lines. Therefore, we can conclude that the overall system efficiency of method 2 is higher than method 1.